negative binomial with parameter Rp. Okay, so I'm actually gonna have as the probability. I'm gonna have the probability of x equal to small s to be x minus 1 r minus 1 p raised to power r p raised to power r and q raised to power s minus r, and of course the state space is actually this. Please, I need you to pay attention. What I want to do right now, I want to show that this is a valid probability mass function. I can ask you to show for other distributions that we have done, but this is a formula. If I want to show whether any discrete probability is valid, is a valid PMF, then I need to show that summation this has to be equal to 1 over the state space. I'm not putting state space right now. Okay, maybe let me just say x start from A to B, for instance, because different probability distribution have different state space. Okay, now when I sum the probability, it has to be equal to 1. That is how to show for every discrete probability distribution. I actually want to show for this guy right now. And I need you to pay attention. What we're going to be doing now is going to be more mathematical. Okay, now I'm going to do this. S start from R, okay, to infinity. If you take a look at that, okay, x minus 1, r minus 1, p raised to power r, x minus r. Who doesn't understand what I just did? This is, I'm actually writing the one for the negative binomial. So take a look at that. Okay, so if I have this guy right now, okay, what I'm gonna do, okay, I have to put into consideration. I have to remember binomial expansion, or remember Maclaurin series or Taylor series, that you guys have done in math. Okay, now I'm actually gonna use this facts. Okay, recall that. Let's say if I have 1 minus w raised to power this, okay, is the same thing as k plus r minus 1, r minus 1, okay, summation k start from 0 to infinity, okay, w raised to power, let me see, raised to power k. Okay, now if you take a look, let me write it here. 1 minus w raised to power r, okay, into summation k start from 0 to infinity, k plus r minus 1, r minus 1, w raised to power k. Okay, you have to, we are recalling we're recalling that. Okay, please pay attention. Like I said, I'm begging everyone, focus the board. Okay, this is theory of statistics. Okay, now I know that this guy equal to that guy. So now I want to write this guy right now. Okay, I got summation s start from r to infinity, x minus 1, r minus 1, p raised to power r, q raised to power s minus r. Now this guy is a constant. I can bring it out. So p raised to power r, then s start from r to infinity, s minus 1, r minus 1, q raised to power that. Take a look at that. Now, if I come here, say let k be x minus r, okay? Let k be x minus r. So what's going to happen? This is going to imply, x to be k plus r, right? That is going to be k plus r. So if I want to write that, I'm actually going to have p raised to power r. Then I'm going to have summation. Now x, k plus r minus 1, r minus 1. Now k start from 0 to infinity now. Okay, when you take a look at this guy, that will be q raised to power what? What is x minus r? K, right? Take a look at that. Now on this, okay, I actually want to apply this. I need you to pay attention. Look at the connection between this guy and this guy. You're actually going to see my Q here is the same as W here. So, which means if I actually want to rewrite this, okay, 1 minus that. So I'm going to do 1 minus Q raised to power that. The whole of this become this. You know, you are using the fact that that equal to that. And this is P raised to power R. So what is this guy? What is, P plus Q equal to 1, right? So this is going to be this and this is going to be that. Okay? And what do you have? That is this. Okay? So this is to show, okay, this shows that Px equal to S is a valid probability mass function. Okay, I can actually to show for any probability distribution when we are talking about a discrete probability distribution. Okay, we can actually show that it's a valid. Because before we can call it, you remember what we did under a probability space and measure. Okay, under the axioms. Okay, we expect the sum of probability to be equal to 1. So that is exactly what we've already proved here. Is there any question to what is on the board? Is there any question? Is there any question to what I've put on the board? Okay, this is how to show that it is valid. Okay, now the next thing that I actually want to do now is using the fact that when you have geometric, okay, in geometric, expected value of S is 1 over P. The variance of S is Q over P squared. Okay, now for negative binomial, for the version, because there are different kind of negative binomial, expected value of S, R over P, the variance of S, R, Q over P squared. Okay, now I want to derive this guy now. But look at the connection they have. When R equal to 1 here, we have here. When R equal to 1, we are here. You see the connection between negative binomial and geometric? Okay? Now, the version of the negative binomial that I'm using is this. The version that I'm using is this. Okay, when you go to textbook, there are different versions of negative binomial. And for geometric, the version that I'm using is this. You see that? Okay, this is the version that I'm using. In some textbook, they're going to have PQ raised to power X. And S is going to start from 0. I can give you that version as well. Okay? There are different versions of of a geometric and of negative binomial. Now, what I want to do now